Okay, this is for lesson 3.8 here, and 3.8 is really just a continuation of lesson 3.7 in the fact that we'll solve more trig equations. Okay, so just put that title on there. Now, these are going to be much more difficult here. And what we're going to need are really some more strategies here. So the first thing I'm going to do, instead of just jumping off into one here, is I'm going to try to make you a list of sort of some strategies that you can use and some examples of those strategies. All right, one of those strategies here would be factoring. Okay, and the idea behind factoring is this: if I can have, say, one trig expression times the other trig expression, and that's set equal to 0, well then that means this trig expression could equal 0, and this trig expression would give me 0. So that means that we would get a lot of solutions out of that, but that would be a way to do it, especially if those trig expressions were different in the fact that maybe one was sine and one was cosine. Now, one that kind of lends itself to that is what we call a quadratic form. Okay, so let me show you guys an example here of a quadratic form. Would be one like this, where we have sine squared x plus maybe 4 sine x minus 5. And so notice the quadratic form, kind of compare it to this, and we'll use that substitution method, kind of like we did in college algebra. We'll call a be sine of x, so we get a squared plus 4a minus 5, and notice how that would factor. Factors of 5 that would subtract to give me 4 would be 5 and 1. And so that's the idea behind a quadratic form there, is so that you can factor it. And once I get to factoring, I can use that zero product rule that says that this expression could be 0 or this expression could be 0. Now, another strategy here would be, and this is not always obvious how to do this, is make all the functions the same. Now, the how part on doing that may be a little bit confusing here, but the why is definitely pretty well understandable. So you make all the functions the same. Okay, so what I mean by that is we want to make them like all sine, okay, or all cosine, okay. I don't want to see sines and cosines kind of mixed in together. So if I have sine and cosine, if I could change my cosines to sine somehow, or my sines to cosine somehow, then I want to do that. Now, the way of doing that a lot of times is by using the Pythagorean identity. So by using a Pythagorean identity, for example, if I have sine squared theta in a problem, all right, if I wanted to put that in terms of cosine, well, I could use my identity here that sine squared theta plus cosine squared theta equals 1. And so sine squared would be equal to 1 minus cosine squared. And so what I could do with a sine squared is I could replace sine squared with 1 minus cosine squared. And there again, the reason why I would want to do that is, well, what if my equation had sine squared and it had a cosine in it somewhere? Okay, I want everything to be either sine or everything even to be cosine. So I could switch this to an expression here that would just have cosine squared instead of sine squared. So there again, that's just using a Pythagorean identity. And you'll use Pythagorean identities on a lot of these problems. Now, another strategy here, and you just have to spot this one, is to use a double angle identity. Okay, so if I see sine of 2 theta somewhere, and I see cosine of 2 theta somewhere, then I can make those substitutions for that. Especially if I had the case where I had cosine of 2 theta and I had a sine of theta in there somewhere, well, I could change the cosine of 2 theta to that identity that had the sign squared in it. So you got to spot double angles there when you see those. All right. Another strategy here is to use a sum to product. And so the idea, especially if it's equal to 0, if I use a sum to product, again, I get this, what I had back up at the top. If I get a product equal to 0, then I can say, well, whatever makes this expression 0, and whatever makes that expression 0, that would be my solutions. Where if it's a sum, see, I can't do that with a sum, but I can do that if I change the sum to a product there, and product being multiplication. Now, another strategy, and this one I try to avoid using this, but sometimes it's the only thing that would work, and that would be squaring both sides of the equation. Now, a lot of times you want to do this when you have, especially when you have a sine and a cosine, and you really can't figure out how to change the sine to cosine. So squaring both sides allows me to get a sine squared or a cosine squared, which leads to using Pythagorean identities. Now, one problem about squaring both sides that you have to address, anytime that you square both sides of an equation, and using this strategy here, you would have to check for extraneous solutions. So some of your solutions when you use this method aren't going to be correct. So when you use that idea of squaring both sides, you have to check your answer. All right, so there's a list of some strategies here. Those are the ones that I could think of that I remember using. We may run into another strategy in a problem here. If we do that, I'll come back and add to this slide, and you can actually take this slide here in the PDF and print it out. Now, okay, so let's look at this one. And so notice we've got square root of 2 times sine squared theta minus sine theta. Now, the thing that I'm going to notice here is they are both sines, but one of them is a squared. So the idea that I'm going to use with this one is factoring. Okay, notice, well, how could you factor that? Because it's not a trinomial. Well, we could factor it by factoring out a common sine here. So if I factored out sine of theta with this would be sine of theta times the square root of 2 times sine of theta. Now notice it wouldn't be sine squared because I factored out a sine, and then minus, now not sine theta, I factored it out. So it would be sine square root of 2 times sine theta minus 1 there because I factored it out, equals 0. So now I've used that factoring idea. So now since I used the factoring idea, what we have is that we have a times b equals 0. So either expression there could be equal to 0. So now I'm going to set them both equal to 0, and it's going to turn into two smaller equations. So I'll have sine of theta equals 0, and then square root of 2 sine of theta minus 1 equals 0. Okay, and now I can solve these individually. Now, that first one, that's fairly simple there. So where is sine? 0. Okay, so the sine would be 0 at 0, and the sine would also be 0 at pi. And I can look those up on my unit circle. I actually just remembered those. So I have 0 and pi. Now, you wouldn't want to say 2 pi there, even though the sine of 2 pi is 0. Notice that they want you to solve the equation for this interval, and they don't include negative, or they don't include 2 pi there. So I don't include 2 pi. I can go up to 2 pi, but not include 2 pi. Now, let's solve or get my solution on the other equation here. Now, this one's a little bit more complicated. So I'm going to isolate sine of theta. I'm going to add that 1 over to the other side here. And now I need to get rid of square root of 2, so I divide by square root of 2. Now I'm going to rationalize that. So 1 over square root of 2 here would be square root of 2 over 2, and that's a little bit more familiar number. So where is sine square root of 2 over 2? So that would be at pi over 4, and it would also be at 3 pi over 4. Okay, so notice got a lot of solutions on these because they break up into two smaller equations. So we got 0 and pi, and then pi over 4 and 3 pi over 4. And notice I don't really have to worry about my general form where I say plus 2 pi k because they're not asking me for that. And notice the other thing is I don't have a coefficient in front of theta. And so that kind of takes care of not having to worry about that. I can just basically on most of these get all this off my unit circle. Okay, let's look at the next one. Okay, now let's see if you can kind of spot a strategy I could use here. So I'm solving this equation. All right. Again, I'm only looking from 0 to 2 pi. So you have 2 sine squared theta plus sine theta minus 1 equals 0. Well, at least they're both sines, at least that. So that's not too bad. Now, let's see if you kind of spotted a certain form there. All right, so did you guys maybe notice here that that was a quadratic form? And so what I'm going to do with this, I'm going to factor it. Now, instead of factoring it like that, what I like to do with these is use a substitution method. So I'm going to do this. I'm going to let A equal sine of theta. So we did some quadratic form ones like this in college algebra where we use that substitution idea to make the problem easier. So instead of 2 sine squared theta there, we would just write 2a squared plus a, instead of sine theta, we're just going to put a there in this place, minus 1 equals 0. And now that's easier for us to solve in that way. Now some people can actually take this and factor it in the trig form. And I can do that, but it just takes me longer to do it that way, and I just do it so much faster with a substitution. Now, so if you want to factor it in the trig form, later on you will probably be able to do that. Let's do this method for right now. So notice I can factor this. Got a leading coefficient. 2 times 1 is 2. Factors of 2 that subtract to give me 1 would be 2 and 1. All right, different signs here, it would be plus 2 and minus 1. And so now we can factor out 2a here. So that would leave me with a plus 1. And then a negative 1 here. That would leave me with a plus 1. And so now finally I'll get a plus 1 times 2a minus 1 equals 0. So our solutions for a here would be a would be equal to negative 1. And a would be equal to positive 1/2. Okay, now those aren't the solutions to my trig equation. That was more of my algebra equation here. So recall that we let a be sine of theta. So now I'm going to substitute that back in and solve for the trig part now. So we get the sine of theta equals negative 1, and the sine of theta equals 1/2. So let's look up on our unit circle here. Where is the sine negative 1? Okay, that's actually only going to give me one solution because it's quadrantal there. And so the sine is negative 1 at 3 pi over 2. And that's the only place that it's negative 1. So just one solution. Now, on my other equation, where is sine 1/2? So that would be at pi over 6. It's also going to have a solution because somewhere else, because sine is positive in the first quadrant and the second quadrant. So looking in the second quadrant, it would also be 5 pi over 6. So there I got 3 solutions for that equation. All right, so notice what I did is I used a quadratic form and a substitution idea to help me out with that one. All right, now let's take a look at this one. Now I don't really care for this one too much because look what we've done here. We're mixing up cosine and sine. And so I really don't care for that because when I want to solve a trig equation, I want them to be all cosines or all sines. Now I'm going to take advantage of the fact that there's some squares in there. So since this is a sine squared, what I'm going to do with that is use a Pythagorean identity and make a substitution. So recall, in my Pythagorean identity, sine squared plus cosine squared is 1. And so since I want something for sine squared there, I'm going to solve for sine squared. So I would get sine squared theta equals 1 minus cosine theta, or cosine squared theta. So now what I'm going to do is replace sine squared with 1 minus cosine squared. Now you might, well, why do you want to do that? Well, it's so that my equation could just have cosines in it. Now watch what happens when I do that. So we'll bring down my first one, negative cosine squared theta. Now plus, now since it's plus, I don't really have to put it in parentheses. If it was minus, I would have to say parentheses and then 1 minus cosine squared. But since it's just plus, we'll say 1 minus cosine squared theta. So we made a substitution there, equals cosine theta plus 1. All right, so now let's notice that we can combine some terms here. Negative cosine squared minus cosine squared. So those are like terms, and I combine them just like if it was a negative x squared, and a negative x squared would be negative 2x squared. So this would give me negative 2 cosine squared theta plus 1 equals cosine theta plus 1. Okay, now let's look at what we can do here. Now I'm seeing sort of a quadratic form here because I have a squared one and just a regular one. So I'm going to set it equal to 0, and I'm going to use that quadratic form, and I'm going to use factoring to do this. So notice what's going to happen with the ones. I mean, they're just going to kind of go away here. And so they'll just cancel off on both sides. Now, again, I'm going to set it equal to 0 because I've got like a quadratic form here. So you have negative 2 cosine squared theta minus cosine theta equals 0. And now I can use factoring here because I can factor out a cosine theta here. In fact, you know, if we wanted to, we could divide out that negative and make them positive, or, you know, I could actually factor out a negative cosine theta. I think I'm going to divide out this negative and make them positive here. So let me give me 2 cosine theta plus cosine theta equals 0. So I just did that. That way that first one was positive. Now, I'm going to factor out a cosine theta. So give me cosine theta times 2 cosine theta plus 1 equals 0. Now I've got the a times b rule here with the multiplication. So if a times b equals 0, a could be 0 or b could be 0. So we're going to set both of them equal to 0 and solve them here. All right, so my first one I'm going to look at and ask here, where is the cosine 0? And so you actually have 2 solutions for that. So that would be at pi over 2, and it would also be at 3 pi over 2. Okay, on my other one, got a little bit solving to do here. I'm going to subtract 1. So that will give me 2 cosine theta equals negative 1, and then divide by 2, so I'll get cosine of theta equals negative 1/2. And so now I'm going to look on my unit circle and see, well, where is the cosine negative 1/2? So cosine is negative in the second and the third, so I'm going to find it in one of those two. So it's negative 1/2 at 2 pi over 3, and it's also negative 1/2 at 4 pi over 3. So now I got those 2 solutions and these 2 solutions. Got 4 solutions to that one there. Okay, so notice that was sort of a substitution with an identity and a factoring strategy that I was using on that one. Okay, now let's notice this one. So there again, I kind of get upset a little bit because this is sine and this is cosine. So I got to figure out a way to make both of those be the same thing, either both cosines or both sines. Now I'm going to use the same idea as I did in the last problem and take advantage of the fact that this one is squared. And so I can use my identity that says that sine squared would be equal to 1 minus cosine squared. And so I'll make that substitution. And now I've got cosines on both sides. Now I'm going to distribute over there. I just don't like the way that looks. So that'll give me 4 cosine theta minus 4. Now there again, what I'm looking at is a quadratic form because I've got a cosine squared and a cosine. And so since it's a quadratic form, we could probably set it up in factor like we did that last one. Now I'm going to set it equal to 0 because that's how you have to factor. And when I set it equal to 0, notice this one right here is negative. So I'm going to pull everything over on the right side. So this will give me a positive cosine squared theta. I'm going to subtract 1 there from that. That's going to give me negative 5. And of course, we put the linear one in the middle. So bring down the plus 4 cosine theta. Now, notice that's definitely that trinomial quadratic form here. So I'm going to let A be equal to cosine theta, and I'm gonna use substitution to get this factor. Now there again, you don't really have to use this substitution, but it does make the problem easier to do that. Now factors of 5 that subtract to give me 4, that's pretty simple, don't have to even split it. That would be 5 and 1, didn't have a coefficient like I had earlier. And so my signs are different, it's going to be plus 5 and minus 1 here. And so we're going to get solutions now of A to be negative 5 and A to be 1. Now this negative 5 one's going to throw you off a little bit, but let's put cosine theta back in here. So cosine theta equals negative 5, and then we'll get cosine theta equals 1. Now in this one, you're going to say, well, where is cosine negative 5? Because I don't see that on my unit circle. Well, let's look at it from an approach of not looking on the unit circle, but how would we solve that with maybe using a calculator instead. So the idea is what we would have to do is we would have to take the inverse cosine of both sides. And so notice that would cancel out there on the left side, but then look what would happen on this side. We should know here that when we try to take the inverse cosine of negative 5, that we can't do that because the domain there is not in between negative 1 and positive 1. And if you tried to push that in the calculator, it's going to say error. So this part of the equation didn't lead me to anything. It's actually giving me what would be called like an extraneous solution. So that one's not going anywhere. So the second half is the only where I'm going to get an answer. So cosine of theta equals 1. Now that's on my unit circle. So where is the cosine 1? And so the cosine would be 1 at 0. And I believe that's it there. I don't really see where else the cosine would be 1 at. Now, again, you can't say probably here 2 pi because it's only going to limit you from 0 to 2 pi, but not including 2 pi. Okay, now let's see if we can kind of spot something on this. There again, I'm getting all ruffled up because that's cosine and that's sine. I don't like that. Now, some of you are going to see the sine squared. You think, oh, I can use a Pythagorean identity because that's what I've been doing on the other ones. But look at something else. Let's see if y'all can spot something else I could use on this one. How about a double angle there? Okay, so you have cosine of 2 theta, which is one of my double angle identities. And so on that one, remember on cosine of 2 theta, you have several choices there for that. And I'm going to use the one that's going to do me the best here. So recall, cosine of 2 theta, it would be cosine squared theta minus sine squared theta. All right, the other ones that I could use would be 2 cosine squared theta minus 1. And then this one, the last one here, 1 minus 2 sine squared theta. And so let's think about what's going to benefit me the most here. So let's note what I've got here. I've got sines, and so I want everything to be sine. So I'm going to change that cosine of 2 theta into this one because it's in the form of sine. So now I'm going to substitute for cosine 2 theta 1 minus 2 sine squared theta in place of that. So I just made a substitution there, and now I got plus 8 sine squared theta equals 4. Now notice these two expressions right there are like terms. That would be like negative 2x squared plus 8x squared. So negative 2 plus 8 would be 6. It would be positive 6. So it would be 1 plus 6 sine squared theta equals 4. Now notice that's really not that much of a quadratic form because it just has sine squared. It doesn't have like sine squared and then another sine somewhere. So I'm just going to isolate sine squared theta. And eventually what I'll do to get rid of the square is take the square root of both sides. Notice I'm going to subtract 1 off both sides there, so I can isolate it there. So I'll get 6 sine squared theta equals 3. And I'll get rid of my 6. And so notice that's going to give me a half over there. So sine squared theta equals 1/2. And now we'll get rid of the square. We'll take the square root on both sides, but you got to be careful doing this here. This will give me sine of theta equals, and you got to remember to say this, plus or minus there. And so that would be square root of 1 is 1, and then square root of 2 on the bottom. And now that'll rationalize to plus or minus 2. No, that's not right. Square root of 2 over 2. So now we're going to look on our unit circle there and ask, well, where is the sign plus or minus 2 square root of 2? So it's a lot of places here. It's actually the multiples of pi over 4, basically, is what our answers are. So this would be pi over 4, and not all the multiples, but I guess every other multiple here of pi over 4. 3 pi over 4, 5 pi over 4, and then 7 pi over 4. So all of those have a sign that would be plus or minus square root of 2 over 2. Okay, now this next one, all of a sudden we get Teddy Tangent showing up to the party. So he kind of spoils things because I want everything to be sine. So let's see how we can talk tangent into becoming sine. So let's see if you got an idea here. And I probably should have put this in my list of strategies here. And so for tangent, we maybe can't change it to sine, but we can get it in some form of sine. So my idea on this one is, let's try this. Let's change tangent to sine over cosine. Okay, and now let's see what we can do about getting it solved there now. All right, so I'm going to do a little trickery here. I'm going to get rid of the fractions. So, and this is kind of say, well, why would you do that? Well, you'll kind of see what happens. But I'm going to multiply both sides by cosine theta. Okay, and so that gets rid of that. And I finally got what I wanted there, is I just got a sine, but then I just kind of created a problem over here because now I have sine and cosine. Well, at least it's sine and cosine and not sine and tangent. Now let's see if you guys can maybe spot something that I could do with this. Notice that you have a sine on both sides, and then all of this is just multiplication. So that being just multiplication over there, what I can do is just divide off a sine on both sides. And now all I have left is cosine. So sine over sine here is just going to give me 1. Those would cancel out. And there again, I can do that because that was all multiplication over there. And so you got negative 2 cosine theta left over here. So now I took one that had tangent and sine, and now it only has cosine. So that idea, this strategy here, I probably should have added it on the front side here, is that if you have tangent of theta, one strategy is to write it as sine theta over cosine theta. Now let me finish solving this. I divide by negative 2 on both sides. So we get cosine of theta would be equal to negative 1/2. Now I'm going to look up on my unit circle here. All right, where is the cosine? Negative 1/2. So that would be at 2 pi over 3. And would also be at 4 pi over 3. So notice most of these equations have two solutions, and it comes from the fact that cosine is negative in two quadrants, in the second and the third. So I got a solution from the second and the third quadrant there. Okay, the next one is a multiple choice one. And so notice you've got loads of solutions on these. Now, notice in this one, they're both signs, but yet those arguments are different. Okay, now what's kind of hard to see on this one, since those arguments are different, I can't put those together. So I couldn't say that was like 2 sine of something. And some of you say, well, hey, how about a double angle right there? Well, yeah, that would take care of that, but then that's not a double angle. So I kind of can't really do anything there. So what you have to see with this is the sum of 2 sines. And so what I'm going to use here is a sum to product identity. Well, why would you want to do that? Well, notice what it's set equal to. It's set equal to 0. And if I have a product, if I have multiplication and it's set equal to 0, then all I have to do is say, well, what makes each expression equal 0? So now let's go with this and let's use that identity there where we're going to do a sum to a product. So this would be the sine of A, let me find it here. The sine of A plus the sine of B. Okay, let me write this down for you so you can see what I'm exactly talking about here. So sine A plus sine B is equal to 2 times the sine of A plus B over 2 times the cosine of A minus B over 2. And so notice that's a product. And so with a product set equal to 0, I can solve that. Now, let's put in our A and B here. So our A and B, and by the way, we're just going to have that set equal to 0 like it is up there. Now, our A is 2 theta, and then our B is 6 theta. Okay, so let's see what happens here. This is going to give me 2 times the sine of, now let's see what happens here. 2 theta plus 6 theta would be 8 theta, and then 8 theta over 2 would be 4 theta. Now, on my cosine one, 2 theta minus 4 theta, 2 theta minus 6 theta would be negative 4 theta, and then negative 4 theta over 2 would be negative 2 theta. So we'd have cosine of negative 2 theta. Now recall here, because cosine is even, the cosine of negative 2 theta would just be cosine of 2 theta. Of course, if that was sine, we'd bring that negative out to the front and would make that negative, or the 2 negative. All right, so now what I've got is just a product. Now I'm going to get rid of the 2. I'm just going to divide it off. So 2, you go away. So 2's gone. Now, since this is a product, all I have to do is just set both of these equal to 0. Now notice a problem that I'm going to have with this is I have those coefficients. And so for those coefficients, you have to look at the general form of the answer to get all the answers that's going to be true here. So let's look here at the first one, sine 4 theta. We'll see what makes it 0 and see what makes cosine of 2 theta 0 also. So we'll have sine 4 theta equals 0. And so let's think about this here. All right, where is sine 0? So sine would be 0 at 0, and it would also be 0 at pi. So we would have 4 theta equals 0. Now remember, with that coefficient there, we're going to have to look at our general form and say plus 2 pi k. And then the other spot there, where it was 0 was at pi. So we'd also get here that 4 theta would be equal to pi plus 2 pi k. Now, we divide both sides by 4. And so now this would give me theta to be equal to, that would be just 0 there. And so that's just going to go away. 0 over 4 is 0, and then 2 over 4 would be pi over 2. 2 pi over 4 is pi over 2. So it would be pi over 2 times k there. And now in just a minute, we're going to have to let k be all those multiples, like -1, 0, and so forth. Now, let's look at my other one. Here, I'm going to divide by 4 here. And so we'll get theta to be here pi over 4 plus pi over 2 times k. All right, so notice we're going to have to let k equal certain values. So let's start it off at 0. All right, so what if k is 0 here? So if k is 0 there, then that's just going to give me a solution of 0. If k is 0 here, then that would just give me a solution of pi over 4. So far I've got 0 and pi over 4. Okay, now let's see what happens when k is equal to 1. So if k is 1 there, then that will give me the solution of pi over 2. Now, if k is 1 here, that will give me pi over 4 plus pi over 2. So let me do that math real quick. Pi over 4 plus pi over 2. So we'll think of pi over 2 as being 2 pi over 4. And so that would be 3 pi over 4. Okay, now let's see what happens when k is equal to 2. All right, so if k is 2 there, so pi over 2 times 2, those 2's would cancel out, and then that would just give me pi. Boy, this one's got a lot of solutions. All right, and then the next one here, we like this k equals 2, and so that would be just pi right there. So that would be pi over 4 plus pi, which would be 4 pi over 4. And so that would give me 5 pi over 4. All right, so probably seeing where all these solutions are coming from in the answer now. All right, let's let k equals 3. It's getting old. All right, let's put 3 in there. All right, pi over 2 times 3 would be 3 pi over 2. So still got some solutions going there. Now, let's put in 3 right here. So that would give me pi over 4 plus pi over 2 times 3 would be 3 pi over 2. Now, if I got a common denominator there, that would be 6 pi over 4. And so pi over 4 and 6 pi over 4 would be 7 pi over 4. Okay, so let's keep going. Let's let k equal 4. All right, so if k is 4 there, pi over 2 times 4 would be 4 pi over 2 is 2 pi. Now 2 pi is too big. I can't include that one. So thank goodness, don't have anything right there. Now let's put it in here. Again, we'll let k equal 4. So that'd be 4 pi over 2, which is 2 pi. And pi over 4 plus 2 pi is going to be too much. So k over 4 is getting too big. And so that's all I've got so far. Now, let's see what the second half's giving me. Okay, so that was only sine of 4 theta. Now I have to do the sine of 2 theta. Really not liking this problem. Okay, so again, this cosine 2 theta, we're going to set it equal to 0. So now let's look, where is cosine 0? So cosine would be 0 at pi over 2 and 3 pi over 2. So now we're going to get 2 theta is equal to pi over 2, and 2 theta, and I'm going to have to bring this to the next screen. So I'm going to do this on another one here. Okay, so there again, we've got this first part. Now we've got to do this second part. So we got cosine 2 theta equals 0. So if we have cosine of 2 theta equals 0, all right, we just mentioned earlier that cosine would be 0 at pi over 2, and cosine would be 0 at 3 pi over 2 also. Now, there again, because I've got that coefficient, I've got to do this and add 2 pi k to it. And that's where all those millions of solutions are coming from. Now, let's go through, let's divide by 2 here. And so this would give me theta equals pi over 2 divided by 2 here would be pi over 4 plus, and then those 2's would cancel out there, plus pi k. Okay, on my other one, same thing, I'm going to divide by 2. And so we get theta equals 3 pi over 4 plus pi k. Okay, now, so let's look at our different values of k. So we get k to be 1 or 0 here. Negative 1 would make it be negative, so that wouldn't work. So if k was 0 right there, then that would just give me pi over 4. And then if k was 0 here, well, that one would just give me 3 pi over 4. Okay, now let's look at k to be 1. All right, so if k is 1, we would have pi over 4 plus pi. And so that would be pi over 4 plus 4 pi over 4 would be 5 pi over 4. On this one, if k was 1, we'd do 3 pi over 4 plus 4 pi over 4 would be 7 pi over 4. Okay, let's let k be 2 now. And so if k is 2, now that's going to get too big. So that's going to give me 2 pi, which is going to go over 2 pi. And that's going to give me 2 pi, which is adding 3 pi over 4, or adding pi over 4 goes over 2 pi. So I've got these solutions here too. So I got a lot of solutions. So let me do this. Let me copy them. And we'll go back and paste it somewhere in here. Well, that didn't work out too well. I guess that would be okay. Just kind of wrote over what I had there. And so let's see. I can't read it. Here we go. Let's do that. So 5 pi over 4, pi over 4, 3 pi over 4, 7 pi over 4. I don't know where that sign came from. Okay. Now, so we got all these darn solutions here. All right. So I got to pick out here which one's going to be the right choice here. So they all have 0. Okay. All right. So they have pi over 3. Yeah, I didn't get a pi over 3. So yeah, I don't think that's going to be right there or there. All right. Now pi over 4. All right. Notice that one doesn't have a pi over 4. All right. And then pi over 2. Let's just look at the difference here. All right, then at pi over 2, we got 3 pi over 4. We got that one. We got pi. All right, 3 pi over 2. We got that one. 5 pi over 4. We got that one. 7 pi over 4. We got that one. And then 3 pi over 2. We got that one. I finally see the one we didn't get. 9 pi over 4. And we didn't get that. So it must be C. Okay. Let's look at the next one. All right. On this one, so notice again, I have a sine theta and a cosine squared theta. Well, I want them to be the same. If I can get them to be, at least one of them to be a sine squared and then a sine, then I can have a quadratic form. So there again, what I can do with the cosine squared is make a Pythagorean identity substitution. So what I'm going to do, and I'm going to rewrite this here, is not say 4 times cosine squared, but what I can put in for cosine squared would be 1 minus sine squared. And there again, I'm doing that because now both of them have signs in them. Now notice, when I had the 4 there, I'm going to have to say 4 times 1 minus sine squared. I'm going to have to distribute that. So let me distribute that. And so I'll get 4 times negative 4 sine squared theta. Now, I hope that you spotted now that we've definitely got a good quadratic form there. Now, I'm going to pull everything over on the left side so I can make that positive. So if we pull that over, that would be positive 4 sine squared theta. And I'll bring down plus 6 sine theta. Now I'm going to subtract my 4. And so that'll give me a positive 2 here. Now equals 0. So now I've got a quadratic form and I can solve it by factoring now. So I'm going to use my substitution. I'm going to let a be equal to sine of theta. So this would be 4a squared plus 6a plus 2 equals 0. Notice I can divide out a common factor of a 2. So that would be 2a squared plus 3a plus 1 equals 0. Now we're going to multiply the ends here. So 2 times 1 is 2. Factors of 2 that had to be 3 would be 2 and 1. Both of them plus. All right, out of my first group of 2a, so leave me with a plus 1, and then a 1 out of the next one. That'll leave me with an a plus 1. And so now we'll get a plus 1 times 2a plus 1 equals 0. So now let's see what makes them 0. So a here would be negative 1, and a would be negative 1/2. Now recall what a was. A would be the sine of theta. So now I've got sine of theta equals negative 1. And also here the sine of theta equals negative 1/2. Okay, notice they don't have coefficients, so I don't have to do all the k business. Now, so where is sine negative 1? All right, let's see, sine is negative 1 at 3 pi over 2. And that's the only place that it's negative 1. It's just one solution out of that one. Now, where is sine negative 1/2? So sine is negative in the third and fourth. So look in the third and fourth here. We got 1 at 7 pi over 6. And then we also have sine is negative 1/2 at 11 pi over 6. Okay, now my next one, all right, so notice there again, I'm all upset. I have sine and cosine. I want sine and sine, or cosine and cosine. Now, let's see if you guys can kind of figure out a way to make that happen. And so notice on the cosine, it's got cosine of 2 theta. So there again, I can use a double angle identity here to make a substitution with. Now, let's look at all those double angle identities again. So I'm just going to look at my reference sheet this time. And so the double angle that I want to use for cosine is the one that has sine in it. And so I'm going to use this double angle identity here that the cosine of 2 theta is equal to 1 minus 2 sine squared theta. And so I'm going to make that substitution. So now this is going to give me 11 minus sine theta equals, now instead of cosine of 2 theta, we're going to substitute 1 minus 2 sine squared theta. Now, you might notice here that this is going to give me another one of these that has this quadratic form. So I'm going to set it equal to 0. So I'll pull that sine squared over here. That's going to be positive 2 sine squared theta. And then bring down minus sine theta. And now we want it equal to 0, so we'll subtract 1 from both sides. That'll give me a positive 10 there equals 0. So notice I'm going to use my substitution method again, where I'm going to let sine be equal to a. All right, so now this will factor factors of 20 that add to give me 1 here. Let's see. Let me think about that. Factors of 20 that add to be 1, that's not factoring. Let me think about this a second. Okay, now so I figured out what happened with this one. I really didn't do anything wrong, but I thought I'd done something wrong because I couldn't get it to factor. Well, it just doesn't factor. Okay, so it's not the end of the world. We have other ways of doing it. It's just going to make this a little harder. So what I'm going to do, since we especially have a leading coefficient here, is I'm going to use the quadratic formula on this one. So first I'm going to find my discriminant. Now my discriminant is really going to tell the story here. So I'm going to b squared minus 4ac. And so let's see, that would be negative 1 squared. So 1 minus there 4 times 2 times 10. And so let's look what this is going to give me here. This would give me 1 minus 80, which is negative 79. Now we recall something about if the discriminant is negative, when I put it into the quadratic formula and say plus or minus the square root of negative 79, well, that's going to be imaginary. And we don't do imaginary numbers, certainly on the unit circle or anywhere usually in trig. So what this means here, since that discriminant is negative, those solutions are imaginary, and so we just have no solution. Okay, next one here. All right, again, we've got another one here where it's got a sine and a cosine. Now, one of the things that's going to really hurt us here is that one of these, neither of them is a double angle, and neither of them is squared. And if I had a square one, I could use a Pythagorean identity. If I had a 2 theta, then I could use a double angle. But I don't have that case here. So what I'm going to have to do is force them to be squares. And so the way I'm going to have to force them to be squares here is I'm going to square both sides. Okay, that's the only way that I'm going to get this to work. So watch here, I'm going to take this and square both sides. And so now when I square this, remember the idea here, if I square a binomial, we square, square, and then we do twice the product. Okay, so let's square. And so when we square, this is going to give me sine squared theta. Now that's what I wanted to see was a square one finally. And then when I square this other one here, that would be a positive 3, and then cosine squared theta. And now we're going to do, again in the middle of this, the opposite product here. And so this is going to be pretty nasty here when I multiply this out. So let's see, that's going to give me twice the product there would be a -2 square root of 3 sine theta cosine theta. And then over on the right side, that would just give me a 1.